let's look at a little more complicated and advanced trig problem. We've got a triangle here. We've got SAS information for the triangle. AC is 8, AB is 12. The angle CAB is 67 degrees. And I claim we can use trig to find that third side of the triangle, even though it's not a right triangle. Well, so how would you apply trig, which we've seen the basic definitions are about right triangles. The key is a very standard piece of advice. If you're stuck on a geometry problem, draw more stuff. And in particular, if you want trig to engage, we want right triangles, so we're going to drop an altitude. Now, there's 3 altitudes we could in principle take from any one of the 3 vertices, but we're just going to see that dropping an altitude from C is your best bet. Now, I already have those made up, so I'm just going to activate the appropriate things. Give me one sec here and sort of redecorate the triangle here. Okay, so now I've dropped an altitude down to D. This is a right angle here. So I've got a right triangle ACD, a right triangle BCD, and I've gone ahead and labeled the 2 parts of that AB side. AD is X and DB is Y. And what's going to happen is we're going to find X first, and then, let's H is always a good letter for that. So let me go ahead and, nope. Let me just rename that. I don't really want that to be called J. So let's rename that H. Okay. So that's going to be the height of the triangle, in other words. Okay. And so we're going to just do this as a multi-step process. And so let's look at what the key trig ratio for X is going to be. X, we know 8. So that in almost any basic right triangle trig problem where a trig function actually gets involved, you're going to know one side and want one of the others, and the other one, the third, is going to be not of interest immediately. And here we want to find, well, actually, let's say we want to find X, because we're actually going to find both X and H. It's going to be useful. But let's say we wanted to find X here. Then that's the adjacent side to the 67-degree angle, and the 8 is the hypotenuse. So that's cosine. So we just write down the definition of the cosine of that angle. And that is going to be X over 8. In other words, X is 8 times cosine. This is something you just want to get absolutely used to. So much of the time, you're going to be pairing a certain side length with a sine, cosine, or tangent. So length times cosine angle is an incredibly common combination. That is absolutely something a calculator can do. We'll let the calculator take care of that. Okay. Now do a reality check. Okay, 3 point something. I'll carry all those digits here. You don't want to round intermediate stuff. I think our book is pretty terrible about almost suggesting you want to do intermediate rounding. It's a terrible idea. So there's our X. We got that. Now we can get H in a similar way. H is the opposite. And so if somebody says, hey, could you just give me an example of what the sine of an angle means? You could just literally write down, well, sine is opposite over adjacent. In this case, that's H over 8. Once again, when we actually cash that out, in terms of getting one side from another and an angle, it's going to be hypotenuse here times sine. So hypotenuse sine and hypotenuse cosine are super common combinations. We're going to let the calculator do that. And we'll just copy that in. Okay, now that should be rather bigger because it's the long side of that triangle. 67 degrees is bigger than 45. And so H is the long side. So that's all passing some reality checks. Okay. So now, what about how do we finish this off? Well, that's where we have to use our other incredibly important tool. Well, first of all, let's see what tool we'd like to use. If we knew Y, we now know H. We don't need any trig over here. And it's very important that we don't know the angle here at B. We don't know the angle here at C. Eventually, we could figure them out if we wanted to, but that's not what's being asked here. Don't assume that like C is a right angle. It's not. Don't assume that B is something special. But we don't need them because once we've got the length h and the length y, oh, we don't have that quite yet, but we will very soon, then we're just going to be able to use Pythagoras to get c. Okay, and this is where people often miss a very, very basic thing, and that is x plus y equals 12. Remember, when you have two segments making up the parts of a long segment, they add to the total. It's not that complicated, but people just kind of miss it. So that means y is just 12 minus x. And so that's 12 minus the 3.1258. Let's have to calculate that. It's not super hard. And so that's, oops, need an equal sign, equals 8.8742. Okay, and now Pythagoras. Let's get that out of there. Z squared is x squared plus y squared. And so that's that. That's right. No, h squared plus y squared. Just kidding, right? Gotta actually use the real number in the actual place in the triangle. So let's copy that just to be careful. So that's squared. Be careful. Squared. Now this is gonna be z squared. It's not gonna be z. We're almost there though. Okay. Please don't put 132. This is a ridiculously wrong answer if you don't square root it. And so z, oops, is the square root of that. And that's about 11.52. Now that's plausible. And that's where you could maybe round. Oops. Something like that, depending on exactly how accurate you want to be. Okay. So that's plausible that it's a little bit less than the base here, but not completely out of line. Okay. So that's a good example. There's so many examples. You don't want to memorize this exact template. The main thing was draw more stuff, usually in altitude, and be okay with a multi-step process and combine the basic trig ratios very often with Pythagoras. And we'll do a lot of variations on this.